Yo, what's up everyone? Welcome to Kinetics Part 2, where today we're going to go over the rate constant and the integrated rate laws. Let's start with a little review from last time. We know from our rate law that the rate is going to equal K, which is the rate constant, times the concentration of A to some power M, which is going to be the order of A, times the concentration of B to the power of N, which is the order of B. One of the most important things here is the rate constant. And the rate constant is almost a little misleading because constant makes it seem as if it's going to be constant regardless of conditions, but that's not true. The rate constant is actually dependent of temperature. And the Arrhenius equation represents its dependence on temperature. So let's break it down starting with what that EA is. That EA is going to be, if you look at a potential energy diagram, the EA represents the activation energy. So the activation energy is how much energy it takes for the reactants to get to the transition state. As long as a reaction has enough, or one of the qualifications for a reaction to occur is whether or not the reactants have enough activation energy to actually form the product. So for endothermic, it's from reactants to that transition state, and it's the same thing for exothermic, from reactants to that transition state. Alright, now that we know what the activation energy part is, what about the other parts? Well, one of the ones is going to be the A part. So even when molecules have the right energy, they will sometimes collide and not cause a reaction to occur. And the A is going to represent, like a percentage of molecules that are going to collide with the right energy and are going to have are going to cause a reaction to occur. Because just because some molecules have the right energy does not necessarily mean that they will cause a reaction to occur. Alright, the other parts are obviously 8.3145, it's your gas constant, and T is your temperature in Kelvin. There's actually a couple other forms of this Arrhenius equation, and one of them being the two-point form, and two of them being the two-point form and the graphical form. The two-point form is probably the more important one, but the graphical form just puts it in a graph. It's in the form of y equals mx plus b, and so you can see that relationship as a graph. Oh wow, I didn't even realize this was wrong. Okay, so the real real formula for this is this: minus EA over R times temperature 1 over temperature 2 minus 1 over temperature 1. So this equation is wrong, my fault. This is the real equation. So again, it helps you relate the reaction rates of two different systems as a function of their temperature and their activation energy and the gas constant. The USNCO actually fucking loves this form, so let's do a bit of practice concerning one of the problems that it comes up in. So a rule of thumb is that a reaction's rate roughly doubles for every 10 degrees Celsius increase in temperature. What is the activation energy of a reaction whose rate exactly doubles between 25 degrees Celsius and 35 degrees Celsius? Well, let's copy down our the formula again. So K2 over K1 is going to equal minus EA over R times 1 over temperature 2 minus 1 over temperature 1. So let's start filling in what we know. So the natural log, we know that the rate of the second reaction over the rate of the first reaction is going to be 2. We're told that it exactly doubles. And we're trying to find the activation energy. We know the gas constant is 8.3145. And then temperature, the second temperature is 35 degrees Celsius. 35 degrees Celsius is 308 Kelvin. And then minus the temperature 1, which is going to be 298 Kelvin. Essentially, all we have to do now is solve for EA, which you can just do that using some basic algebra. And once you solve for EA, your EA is going to be about 52,897-ish. But remember, this is in joules. And so in order to find in kilojoules, you just divide by 1,000, and that's about 52.9 kilojoules per mole. And that is answer choice A, which is in fact the right answer. Let's move on to units for rate constant. So depending on your overall reaction order, you're going to have a different unit for K. For 0, like a reaction order of 0, it's going to be molarity over seconds. For 1, it's 1 over seconds. For 2, it's 1 over molarity times seconds. And it just keeps going on. So for 3, it would be 1 over molarity squared times seconds. And then for 4, it would be 1 over molarity cubed times seconds. And just on and on. And it kind of makes sense why it would be like this. As long as you realize that the unit for rate needs to be molarity over seconds, everything all works out. So think about what rate is. So rate is going to equal K times the concentration to X over the other concentration to Y. So let's say our reaction order is 2, and we split it up like there's a coefficient of 1 on the A and a coefficient of 1 on the B. Well, that is going to come out to, this little bit is going to come out to molarity squared. In order to negate that molarity squared and to get molarity over seconds, we need to multiply this value by 1 over molarity times seconds. That cancels out and you're left with molarity over seconds. So essentially the unit for K is what helps balance out the unit for the A times the B. And regardless of what reaction order you have, the unit for K needs to be something such that the rate, the unit for the rate, is going to be molarity over seconds. And again, this does actually come up on the test. Let's look at this problem. The rate constant K for the reaction is 1.63 times 10 to the negative 6th, 1 over molarity times seconds. What is the overall order of the reaction? Well, if you just look at your table right here, that's going to be this one, which tells us that our reaction order is 2. So as long as you know that the rate constant has different units, this is kind of like a free question. And C is actually the right answer. So up until this point, we've been dealing with this rate law. What this rate law does not do is take into effect like the effect of time. And so what does take into consideration the effect of time are going to be your integrated rate laws. So your integrated rate laws are what you get after doing some calculus on the rate laws, and they relate the time and the concentration of reactants. And there's different rate laws for each order of reaction. So let's go over the 0 order, the first order, and the second order. For the 0 order, this is going to be the rate law. You're going to realize that the integrated rate laws are all in the form y equals mx plus b. In this case, the y is going to be equal to this bit. The m, which is the slope, is going to be equal to minus k. The x is t, and then b is the initial concentration of A. We'll get a bit more practice as to using this, but essentially for 0 order reactions, if you were to plot the concentration of your molecule or whatever, of your substance over time, you realize that it would be a negative straight slope as long as you were to plot the concentration over time. The half-life for 0 order reactions is going to be the initial concentration over 2 times K, which is your rate constant. For first order reactions, it's a little different. In this case, it's still y equals mx plus b. But in this case, if you plot the natural log of the concentration of A over time, you'd get a negative linear slope. And the half-life for this one is going to be the natural log of 2 over k. Again, the slope here is going to be negative k. And we'll see why the slope of the first order and the second order being negative k is important. It's because the slope for the second order is going to be a positive. So in this case, 1 over the reciprocal of the concentration of A, if you were to plot that against time, you would have a positive linear slope. In this case, the half-life is 1 over the K times the initial concentration. And of course, it's going to be in the form y equals mx plus b. Again, the slope this time is K. So if you were given on a test that the 1 over this plot, if you were given this plot and you were asked what is the order of this reaction, well, you couldn't tell because that's a negative slope and you know second order reactions have a positive slope. And so what do I mean about being able to determine the order of a reaction if you were to see their graphs? Well, let's take a look at this problem. For an irreversible reaction A to products, the graph of 1 over A as a function of time is linear. What is the reaction order in A? So we're told that the graph of 1 over the concentration of A as with respect to time is linear. So it could be something like this. And the fact that we're told that 1 over the concentration of A over time is linear, that tells us that it's going to be a second order reaction. Now, if we were told that the concentration of A with respect to time was linear, then we would know that would be a zero order reaction. And if the natural log of the concentration of A graphed as with respect to time was positive, then we know that would be first order. But we're told that 1 over the concentration of A is linear, and that is characteristic of a zero order reaction. So our answer here is C, and that is the correct answer. I'm going to do a bit of practice using like a kind of algebraically. So polonium-210 undergoes alpha decay with a half-life of 138 days, forming the stable isotope lead-206. How much time would it take for the activity of a 210 polonium sample to decrease to 15% of its initial value? The thing you need to know about radioactive decay is that it's always going to be a first order reaction. And so remember, our equation for first order is going to be this equals minus KT plus the natural log of A0. And from here, we can do a couple things. We know that a sample decreases to 15% of its initial value. So let's just say the initial value was 100 molar, and our final molarity is 15 molar. That's 15% of 100, so 15 molar. And so if the natural log of our concentration of our final concentration, that's going to be 15 minus K times time plus the natural log of our initial concentration, which is 100. So we need to figure out time, but in order to figure out time, we need to figure out what K is. Well, we can figure out K if we look at the half-life equation. So the half-life equation is the natural log of 2 over K. We know our half-life is 138 days, and that's the natural log of 2 over K. The natural log of K is the natural log of 2 is about 0.693. And so if you were to solve for K, you would get that K is going to equal 5.02 times 10 to the negative third. And so what we can do now is we can plug that all into our equation. 5.02 times 10 to the negative third times temperature plus the natural log of 100. And if you solved all this out, you would get that time is about 377. And since our unit for time here that we used was days, it would be 377 days, which is answer choice D. And that is, in fact, the correct answer. So what integrated rate laws allow you to do is take the initial rate, or the initial concentration, and as long as you know your rate constant and like a time, then you can find out the concentration of that reactant at a different time. And that's the magic of integrated rate laws. Okay, that's all I have for this lesson. I hope you learned something about integrated rate laws and just the rate constant. And I hope to see you later for part 3. Thank you for watching.